We studied waves in AP Physics 1, and this is our first video on waves, but these are different waves. These are light waves in AP Physics 2. So this will be our first video on light waves, and we're gonna start with electromagnetic waves. Many people confuse sound waves with radio waves, one type of electromagnetic waves. However, sound waves and radio waves are completely different phenomena. Sound creates pressure vibrations waves, and it only can happen in the matter where there's matter to push the energy across for the sound, like air, water, or even earth or earthquakes. So this would be something that sound can travel through. So sound needs matter. And radio waves are electromagnetic waves like visible light and infrared and ultraviolet and X-rays and gamma rays. So these all rays are electromagnetic waves, and they don't need a medium or stuff to travel through or propagate through. They can travel through a vacuum such as outer space. For instance, a radio works because sound waves played by a DJ at the radio station are converted into electromagnetic waves, then encoded and transmitted in the radio frequency range. The radio in your car receives the radio waves and decodes the information and uses the speakers to change it back to the sound waves, bringing sweet music into your ears. So the sound waves are mechanical waves. They need medium. And radio waves, so we have here, and I have in the picture that you see, we have here radio waves, microwaves, infrared waves, visible light waves, ultraviolet waves, X-rays, and gamma rays. They're all light waves. They're all light. Even though we think visible light is light, it's only part of electromagnetic radiation. Everything in here is light, and it travels at the speed of light, which is 310 to the 8 meters per second. So all of these electromagnetic waves travel at the speed of light, 310 to the 8 meters per second. The radio waves have the longest wavelength, so they tell you the wavelength in meters of the radio waves. The microwaves are in centimeters. They have smaller wavelengths, and the infrared in almost not micrometers yet, but close to micrometers, and the visible light is already in micrometers, and they tell you the size of them. So the radio waves, the size of the buildings. The microwaves start with human size, the length, and ends up with the butterfly size. The infrared light is about the size of a needle point, and the visible light is the size of the protozoans, and protozoans are a single-celled organisms. And then we have ultraviolet, they are the size of the molecules, X-rays the size of the atoms, and gamma rays the size of the nucleus. So the ones that are going to the higher frequency, so it starts with low frequency and large wavelengths, long wavelengths, and it goes to the higher frequency at the end. So the ones that are ultraviolet, X-rays, gamma rays, they are all at the higher frequency, and this is why they are dangerous to our body, because if they go through our body, or even through like X-rays or gamma rays or ultraviolet light, when they go in contact with our body, they destroy our molecules. For instance, extremely high energy of gamma rays allows them to penetrate just about anything. The gamma rays can even pass through bones or your teeth. This makes the gamma rays very dangerous, and they can destroy living cells, produce gene mutations, and cause cancer. And the deadly effects of gamma rays can be used to treat cancer. And all these waves, electromagnetic waves or radiation, comes from the source of it, which is the sun. we have nuclear reaction in the sun that produces all these types of waves, and gamma rays are given by radioactive atoms in the nuclear explosions. They are also given off by the sun and other stars, and as well as collapsing stars and gamma ray bursts. Fortunately, gamma rays from space are absorbed by the Earth's atmosphere before they can reach the surface, because gamma rays has high frequency. When the high frequency rays enter the atmosphere has the molecules, so they scatter through the atmosphere and don't get through to harm us. If gamma rays could get through the atmosphere, they would destroy almost all living organisms on Earth because they have so much energy. So high frequency rays have high energy. So as you see here in the picture, the electromagnetic waves vary in their wavelengths and frequency. So at the bottom you see the frequency. So the frequency of the radio waves is 10 to the 4th hertz, measured in hertz, and for the beginning of microwaves is 10 to the 8th, and then it goes 10 to the 12th at the beginning of infrared, and in the middle of like visible light we have 10 to the 15, 10 to the 16, and that's all in hertz, how many times per second you meet this the peak of the wave. And gamma rays is going 10 to the 20th, so they have higher frequencies, and waves have more energy, the ones that have higher frequency. Of all electromagnetic waves, gamma have the shortest wavelength and highest frequency. Because of their very high frequencies, gamma rays have more energy than any other electromagnetic waves. The sources of gamma rays include radioactive atoms, nuclear explosions, and stars. Gamma rays from space are absorbed by Earth's atmosphere, and gamma rays can destroy living cells, produce mutations, and cause cancer. They can be used to treat cancer as well. And you also can see that how the frequency and relates to the temperature. So the temperature of the object at which this radiation is most intense, the wavelengths emitted. So we all the living organisms, or all the matter that has temperature, emits some radiation. So we don't see our emitted radiation, but they need infrared camera to be able to see our emitted radiation. So we do emit radiation in infrared waves length. So you see from the bottom picture, it has a thermometer, and it shows you like the X-rays have the produce their radiate their energy at this temperature, or let's say microwaves you will be able to detect at this temperature. And sometimes they take pictures of space in different wavelengths because you see different pictures of space. Here, for instance, I found you our planet Earth in different spectrums. So you see it in infrared, visible, ultraviolet, extreme ultraviolet, and X-ray, and gamma rays. So the same, we can see space in different spectrums, and can see different details taken under different wavelengths or frequencies. Here is Carina Nebula that is taken by Hubble telescope, with visible on the left side and then in infrared range on the right side. Another beauty of taking pictures at different wavelengths and frequencies. And just as we did in our AP Physics 1, the light waves still have interference. So when they off the phase, so if these two waves are off the phase, they cancel each other, so you will have no wave, or you will see darkness. Or if they are in the same phase, their troughs and their peaks are at the same, happen at the same, or crests happen at the same time, so you will see increased amplitude for constructive interference. Also, what's interesting, light can behave as both a particle and a wave, and since the days of the Einstein, scientists have been trying to directly observe both of these aspects of light at the same time. And double slit experiment is one of the ways where you can see how the light behaves as a wave. And yet light is behaving as a particle because photons carry energy of light, and the energy of the photon depends on the wavelength. So the longer wavelengths of photons have less energy, and shorter wavelengths photons have more energy. And red photons, for example, have less energy than the blue photons. Einstein was the first one to explain what is happening. He theorized that electromagnetic energy comes in packets or quanta, which we now call photons. So light behaves as a wave and as a particle depending on the circumstances. And this effect has been observed in different phenomena. When the light reaches different mediums, it can travel through different medium, and it does slow down. Its frequency doesn't change, but its speed will change. And when it reaches the different surfaces, there will be the incident ray, like you see in the picture on the left, and the reflected ray. So the incident ray has an incident angle with a normal. Normal means perpendicular to the surface. And the reflected ray is always equal to the incident ray. But in reality, things are not always smooth. And because of that, sometimes when the light is reflected, you can see different colors because they are affected by the surface. And also, if the light travels from one media to another, it can go through refraction. So you have here the light going in this direction and then refracts in a different media. So when it comes from denser medium to the less denser medium, the angle of refraction increases. And when you have the light, when it reaches critical angle and it's coming from the denser, not from the lighter or less dense area, to a less dense area, it can reach a critical angle. So there can be a critical incident angle at which the light doesn't come out from the medium anymore, and can be fully reflected back. So this would be refraction, critical angle after which you have total internal reflection back into the medium where the light is coming from. Questions about critical angle appear a lot in our lessons, so you will see critical angle very often. They will ask, what is the critical angle? And what that means, after this angle, everything else is going to be internally reflected. So that means incident angle is some angle, and after that incident critical angle, you will have refracted or reflected light angle is equal to 90 degrees. Also, as before in AP Physics 1, we looked at reflection of the waves when they reach different medium. So if the wave goes into the medium that is at which the wave or the medium, like here in the rope, is attached, the wave is going to be reflected 180 degrees, so 180 degrees phase shift. If the rope is not attached and can freely move up and down, then the wave is going to be reflected in the same phase as it came. Then if you have the medium with less dense, the same as we did water and air for the light, so if you have the medium that is less dense and coming into the higher density, some of the wave is going to be reflected back, but it reflects phase shifted from because the medium was denser, and some of it will continue with the same phase as it was coming. Then if the wave is coming with the higher density to the lower density medium, then it will continue with the higher amplitude because it had energy. Now that energy transferred through the low density medium, so it can achieve that higher amplitude, but it also will be reflected with the same phase. So here you had phase shift, and here you have no phase shift. And I also have a lot of conceptual videos included in our lesson that I hope you watched before you watch my videos. Here's an interesting phenomena. It's called thin film interference, and it occurs when the light wave reflecting off the top and the bottom surfaces of a thin film and interfere with both with one another. So the light that is coming and reflecting and the light that is refracted and then reflected meet each other in the air, and they have this effect where you see like a rainbow. This type of interference is the reason why the thin films such as oil or soap bubbles form colorful patterns. Here's another example. This one is called refraction of the light, and the different colors correspond to the light of different wavelengths and frequencies. Like the red light has the longer wavelength, and the blue one or purple has the shorter wavelength, and the red one has the lowest frequency, and the blue or purple have the highest frequency of the visible light. So these colors are refracted to different degrees. Here I spoiled our picture a little bit and I added the matter so you can see how this affects the light. So when the light is coming from the air where the matter is spread away, the molecules spread away farther away from each other, and comes into the medium that is denser like the glass or plastic, then the wave length is going to change. Frequency doesn't change because frequency is something that is created by the source, by the sun, and it stays with the matter, with the light when it travels. But when the white light enters the medium, the red light has the longest wavelength, and because it has the longest wavelength, it interrupts with the medium the least. So it gets affected the least, it slows down the least, and so it comes out faster. But the blue light or the purple light interrupts with the medium the most, and so by the time it comes out, it gets affected the most. So it gets the angle of how it comes out is affected the most, when the purple light as well. This is another thing to look at, because when you think about why we see the sky blue, many people say because we have ocean. Well, in the desert you don't have ocean, you still see the sky blue. And you see the sky blue because when the white light comes, the visible light comes from the sun, the atmosphere interacts with the molecules of the sun. The light interferes with the molecules of the atmosphere and scatters through the sky. And the red light does not interact as much because it has longer wavelengths, but the blue light or purple light interferes the most. So we see the blue color as the sky, and only see the orange or red color when the sunset happens, because the light travels through the longer distance during the sunset, longer distance of the atmosphere. And there's the reason why we don't see the sky purple. It's the way our eye works. So the two spectra that have the same cone in the eye, the way it senses the different colors, and in the research published, people expressed that the sky's combination of violet and blue come together, and the way our eye senses it, it senses as the blue color, not the purple color. Our eye cannot just tell the difference between the complex spectrum, and one of is the mixture of the purple blue or pure blue and the white. In some animals can see the sky color as different color. And actually there are a few animals that see colors differently than we do. Let's say spiders or jumping spiders see ultraviolet and green color differently than humans, and insects like bees see ultraviolet blue and yellow different than humans, and fish must see just two colors, and birds have see 5 to 7 colors. Mammals like cats see 2 colors but weakly, so they don't have as good with color vision as people do. And the same with the dogs. Rabbits see the same for blue and green, but also have different colors than people. And let's say the monkeys, some monkeys cannot see red color as we do. And it all depends on the structure of the cones inside of our eye, how we perceive the color that is coming, the frequency that interacts with the sensors of our eye. Here are 3 more examples of refraction. On the left, you see a coin inside of the water, or it's a good one to do inside of the bowl. So if you put the coin inside of the bowl and you move your eyes to the point where you cannot see the coin, then you fill up the bowl with the water, and all of a sudden you see the coin. Another example is where you see your feet to be closer to you or appear shorter to others when you're inside of the pool, or when you can put a straw in the water and it appears like it is broken. So all of these are the effects of the refraction. We will use Snell's law formula to describe the relationships between the angle of incidence and refraction. And when referring to the light or other waves passing through a boundary between 2 different isotopic media, such as water and glass or air, we will use the Snell's law. And in this section, you need to know certain things about the formula and the variables that are in the formula. So one of them is n, and that is the index of refraction. And what you have to remember about n, the index of refraction, it is the relationship between the speed of the light in the vacuum over the speed of the light in the medium. So n is always greater than 1 because the speed of the light in vacuum is faster than the speed of the light in the medium. And always remember, the speed of light changes in the medium, the frequency never changes, and the wavelength is changing. So if you remember, the velocity of the wave from AP Physics 1 is equal to lambda times the frequency. So if the wave speed is decreasing, then the wavelength will be decreasing, and the frequency depends on the source. So again, it's good to know and remember that n is the relationship, it's a proportion of the speed light to the light in the medium through which light is traveling. And the Snell's law states that when let's say you have medium n1 and you have medium n2, when the ray comes and it has an incident angle and it has refracted angle. So if the medium is thicker than the medium 2 is thicker than the medium 1, then the angle of refraction is going to be smaller, but the angle of reflection is always the same as the incident angle. So the Snell's law says that n1 sine theta 1 is equal to n2 sine theta 2. And because n is the speed of light in the vacuum over the speed in the medium, and then you have sine theta 1, and then the n2 is the speed of light in the vacuum over the other medium, then you have sine theta 2, then the speed of light can be cancelled and you get the next formula. Also, you know that since you have sine theta 1 and v1 is equal to sine theta 2 and v2, I can replace my v with lambda 1 and frequency. Frequency doesn't change. And then for the second one, because it's the same wave with the same frequency, I have lambda 2 and the frequency. And again, frequency can change, it can be cancelled from both sides. Frequency doesn't change, frequency can be cancelled from both sides, and I get the next formula. So I can use this formula, or I can use any of these formulas, so they all derived one from another. And here's an example of the problem in number 1. They ask you which of these three pictures shows the correct light traveling path, and you can see that C is the one, because if you have the normal to the surface, then the incident angle has to be greater than the angle of refraction, because the medium, the shaded medium, the blue area medium, whether it's glass or water, is thicker than the one that is air where the light is coming from. Here's another example of the refraction when you see the fish to appear in a different place than it is, actually higher than it is. So you always, if you were with a spear trying to catch the fish in the ocean, you would want to point lower than you see the fish in order to be able to catch the fish. And the picture on the right shows you the effect where you see that the wavelength is changing, like I explained earlier a little bit, where the wavelength is changing and the velocity is changing, but the frequency of the light is not going to change. So in this question, they say that the wave length of 589 nanometers produced by the sodium lamp traveling through an air as incident on a smooth, flat slab of crown glass, and incident angle is 30 degrees with the normal. So you have light is coming and this is the normal, so here is 30 degrees, and then it's going to be refracted. So they ask you the index of refraction with the glass. So the air, n is equal to 1. So again, n is the speed of light over the medium velocity, and for air we take 1, and for the glass it's 1.54. So this is n2, this is n1, and Snell's law says n1 sine theta 1 is equal to n2 sine theta 2. So n1 is 1, then I have sine of 30 is equal to n2 is 154, and then sine theta 2. So theta 2 or sine theta 2 is equal to sine of 30 divided by 154 and equals to 0.32 and if I'm looking for theta 2, I need to do arc sine. It's the one on your calculator with the -1. It doesn't mean it's to the negative first power, it's the inverse function of 0.325. So theta 2 is equal to 19 degrees. So you see that the angle of refraction is smaller than the angle of incidence because the medium that it's coming to is thicker than the one that it's coming from. In this question 4, they say if the light ray moves from the inside of the glass toward the glass air interference at an angle of 30 degrees, interface of 30 degrees to the normal, determine the angle of refraction and the index of refraction of the glass, air to glass is 155. So here I have the light coming out of glass and into the air. The angle of refraction is going to be bigger because the air is thinner than the glass. And they give you index of refraction of the glass and air is 155. And if my 1 becomes glass and my 2 becomes air, so I have Snell's law, then I plug in index of refraction for the glass, sine theta for the glass, incident angle, and then I have the index of refraction for the air and the vacuum, and which is 1, and then I'm looking for theta 2, which comes to be 50.8 degrees. I will finish our first video on light waves 1 at this point, and it was mostly introduction to electromagnetic radiation and refraction and Snell's law, and I'm going to do more practices with Snell's law in the next video 2, and follow the links if you want to see those. And thank you for watching this one, and I will see you in the next video.